Okay. I can't leave this on. At some point I have to lecture. So what are we talking about today? Tensors. Yeah. So we talked about, my intention was to talk about tensors, but I only could get to the doorstep. So now I'll define tensors. And again, I may have changed numbers, but it's somewhere around definition, and I'm combining through two definitions together. A tensor, so again, you have coordinate transformation of this type. And these guys never show up in vector, dual vector transformation, right? So we have transformation rules for vectors, which is what? Suppose you have a mu. Under such a coordinate transformation, a bar mu becomes lambda mu mu, a mu, and dual vector, please confirm that it is correct. It is a little bit of tensor gymnastics or index gymnastics that you have to get used to. After a while, it will just be very clear. So now I'm going to define an arbitrary tensor. Even this can be generalized, but I'm going to define both a tensor field or a tensor at a certain point. So if you have, again, Minkowski amount of space-time, you can define it at any point P, a tensor. Okay? So this tensor will have multiple index. I can't draw a vector space to it because it's not a vector space, it's a tensor space. Okay. But I can write down the object. So I could have this weird tensor over here at this point. I can write a tensor T, I don't want to draw it as an arrow. Okay. But I can just as well say we have a tensor field. For every x, there's a tensor. So I'm going to define a tensor field. Well, how do I define it? Exactly in terms of these transformation equations. Now remember, if this is actually a field, I can give more space here. If it depends, bar mu. If this tensor is at a point x, sorry, if that vector a mu up or down is at a point x, it's the same vector in the new coordinate, transform space, but it's at the point, the old point x is now called what? Right? And that makes it a field. In the new coordinate system, it'll have components x bar mu. But they're physically the same point. So I'm going to write a tensor just like this in a new coordinate system. Okay, so it'll be T bar. Instead of one index, we can have many indices. So I call them mu1 all the way to mu r, just r is any number. And it could also have lower indices, and I call them nu1. All the way to nu s. Okay? This is a tensor of type Rs. It has s many covariant or dual indices and r many contravariant indices. And it's literally a multiple copy of these two guys. So for every up index, I'll have these guys. For every low index, I'll have S many these guys and R many these guys. Okay, so just to make sure how I used alpha and beta phi. So I would have alpha mu1, alpha 1, all the way to lambda mu r, alpha r, and then I would have nu 1, beta 1, multiplied all the way to nu s, beta s. I hope that's correct, this. And this will be t alpha 1 through alpha r, beta 1 through beta s. And finally, I would put x over here and x bar over here. Anything that transforms by this rule is a tensor of type Rs. You don't attach at the moment too much weight or difficulty or meaning to it at the moment. We'll slowly develop an intuition for it. I'm not saying that there's no meaning and weight to it, but it's just multiple indices. What are they? Well, whatever they are, they transform like this. If I give you a tensor, and I have to give you a tensor in a certain Minkowski frame, a certain inertial coordinate system, in a certain Lorentz frame, and then if I ask you what's that tensor in another coordinate frame, this is precisely what you would do. First you would solve for lambda, the Lorentz transformation, and then that's for these guys. For here you would solve its inverse. And remember, if you have alpha 1 through alpha r here, and alpha 1 through alpha r here, what are you doing? You're summing them. Same thing with beta and beta. Okay? Any questions?
For the lambda mu1 alpha 1 and then directly next to it is the next set of lambda going to r. Is that supposed to be mu r alpha r?
Yeah.
Mu1 alpha 1, yeah, mu r
Okay.
alpha r. Mu 1 beta 1 mu s beta s. So the next one is a problem. Again, I'll state, I don't think you have to do anything to this problem. We want to recognize something. And this is what the problem says. Suppose I have this eta. Well, let me put it this way. Let me put it over here. And with down index. And I chose alpha and beta. Okay? Suppose I want to transform that. How will I transform this? So these are two down indices, right? And so to transform down indices, I would pick two lambdas, and I would put alpha over here and beta over here. And what did I pick up? Mu nu sounds good. Mu nu. Is that correct? If I did this, I would get what? Lambda bar, eta bar in, what would be the index of eta bar? Mu nu. And like I said, that's not the problem. That's how, if eta is a tensor, that's how they would transform. Right? But we know what that left-hand side is. Who can tell me, without looking at the notes, you've seen it, it is in your notes, who can tell me what that guy is going to be?
It's just equal to eta.
It's just equal to eta.
No matter how much you rotate it, it's still eta.
We have shown that this is equal to that. That's one of the defining properties of eta. So eta is not only a tensor, it's an invariant tensor in special relativity. Yeah? In fact, the lambdas were constructed so that eta goes to eta. So I don't know what's there to show, but I've stated it as a problem. Maybe I should state it as a remark. Most of my problems are that way. It's like, just connecting the dots. You've seen this before. Okay. Now, here I did a very nice ordering of indices. I put all the up first and then all the down first. You don't really have to do it that way. You can mix indices any way you want. So for example, I just write I call them mixed tensors and tensor products. So I wrote an object like, you can have a tensor like this. It has one contravariant index and two covariant index. So how would something like this transform? But before I do that, I also mentioned that we can multiply tensors, tensor product. You can write up, and we'll do a product. I'll do S mu nu, and I can multiply these. But how do they transform? Well, they each have their own transformation rule. So for example, this is a tensor with, again, two contravariant indices and two covariant indices. But you would multiply exactly in a certain sequence to see how they transform. Well, let's just do that. I'm going to run out of indices, so let me look at my notes so that, we don't have to, I can label it anyway. Let me go this way. So I want to see what this would transform, how this object would transform. And I called it, well, it has to be an S bar and T bar, and all I need is the left-hand side. Well, I actually just call it S mu nu and T bar alpha beta. How do you think this should be? So the goal would be for me to pick new indices. I took mu, nu, alpha, beta, gosh. So I called it A, B, and C, D. That's really no good because we've been using these Greek letters. So can you give me 4 Greek letters? Gamma, lambda,
Delta,
sigma, and delta. Okay, so then I do this. I know I need so let's do S first. Right? So S has gamma here, so I put gamma here. I have to end up with mu here, so I put mu here. Are we good? Tell me what the next one is going to be.
it's going to be lambda nu.
Lambda nu upstairs or downstairs?
Nu will be downstairs.
It will be downstairs, and therefore it goes here. And then what will be the upstairs?
The sigma. No, sorry. Upstairs will be alpha. Upstairs.
We're doing
sorry.
S first.
Yeah, sorry. For S, it'll be this will be gamma. No, sorry. Not
No.
gamma.
First of all, gamma
goes on
like-
top. Yeah, gamma does go on top, right? And nu goes on top.
No, here.
Lambda.
Lambda.
Jesus, I'm going crazy.
Yeah. Okay, so I will. Someone else. Kate, you want to tell me what the next lambda is? Yeah.
This is for T-bar now, right?
It is for T bar. I need a little space here.
Would it be alpha? up
Got it?
top,
Yeah.
And then delta? Or would it be sigma?
Sigma, because
Oh,
what
yeah,
you're trying
okay.
to do is convert this sigma to alpha. So
Okay.
you connect it. See, it is being summed.
All right.
Okay, Veronica?
Oh, Lord, okay.
You want to get rid of delta and replace it with
Beta.
beta.
So.
So it is delta and beta. That's how you go. And now the question is, where would you place them?
Beta on the bottom.
Beta on the bottom, good, because it is on the bottom
Yeah.
here.
And then delta on the top.
Delta on the top. Now, remember, the ordering is very important. Okay, this looks a bit scrunched, so let me. Yeah. Is everyone clear? David, here? Zachary, are we on board?
Oh, so there is a pattern to how it
Yeah.
maps, okay. Okay.
Yeah, there's a, more than that, there's a definite pattern to it.
Okay, I can follow that.
Now, what, yeah, there's a definite pattern, let me stop there. You can choose any of this to be any different. Tucker, are we good?
Yeah, I see the pass on the pattern, like halfway.
Zachary, what part is unclear?
I don't know. I don't know what the pattern is.
See, on the left side, if the mu is up and it's the first, it's gonna be up and on the first. If the mu is down and the second, it's on the second one, it's gonna be down. It's gonna be exactly where it goes.
So the first
On the
lambda,
left side.
yeah, the first lambda is gonna have the first up for us. The second lambda is gonna have the first, or the down for us, and then so on and so forth. And it's just like converting between the two.
Yeah. Well, I can't write it. It's like there's
Listen, so here's what it is. So, for example, T, I have to get rid of sigma, and I have to end up with
Alpha.
alpha. So the only way to do that is just look at that one piece at a time. So it's end up with alpha, get rid of sigma.
And we want alpha on the top, so we want the first index.
Correct. Alpha is on the top, so it's always the first index, but it's the top and bottom that you have to worry about. So let's exactly do that. Nu, it's a lower index. I have to end up with nu.
So your first index
And-
is lower nu.
And I have to get rid of lambda. I don't have a choice, so I have to end up with nu, get rid of lambda. Yeah? Now there's a pattern. So I'm just doing that as many times as needed. Again, the only thing is, you saw it now, so it's clear in your mind. But then, if the lecture continues, we did something else, or tomorrow we go, what was that? You just have to revisit it.
So each one has two lambdas corresponding to it, right? Or well, can it have more?
Well, no, so since we have to get rid of lambda, we have to sum lambda out. It's a dummy variable. We're summing through all the values of lambda.
Okay.
Yeah,
But only if there's more indices on
Yeah.
each tensor,
yeah.
then you'll have more lambdas.
Yeah, so remember, when you sum it out, that index is gone. You're summing it. When you make upstairs and downstairs to be the same index, you're summing it through all the values. It is gone. So at the end of the day, I know lambda has disappeared, so I can call this theta as long as I call this theta.
So it just doesn't matter because it goes away.
Yeah, it's a dummy index.
Is there any way to like turn the multiple indices into one index?
I mean, they use a multi-index notation, like they would like mu, which is supposed to be, it has no real advantage.
Oh, yeah.
But once you've become an expert and you want to make symbols look smaller and smaller, there's no real advantage to that. Compactified notation.
I'm just thinking like, it'd be simpler if you could, but I wouldn't actually be simpler. You're doing the same.
Yeah, but then upstairs, downstairs becomes a real hassle. But there's a lesson to be learned here from what I just said. What I said was, when you have one upstairs index and one downstairs index on one side, it doesn't show up on the other side. It has summed itself out. So let me ask you this. What is this object? Suppose, don't write this part down. Suppose this is a tensor, right? And it is. But if I did this, what is this object?
It's just S of mu.
Yeah.
Not S of mu.
Or sorry,
it is
S
it
with
is a vector.
Yeah, it's just a vector. Oh, yeah, it is just a vector.
You summed it out.
So a tensor with two identical indices
Yeah.
is just a vector.
Yeah, that new is,
If it's
but
left- if it's
I'll
left
clarify
one.
this,
It's
I'll
left
clarify this. So, on one hand, I will do so claim, I didn't write it as a claim, but S bar of mu is equal to lambda mu alpha S alpha mu. If you contract it, that index has gone away. Yeah.
So they can sum over themselves in the same tensor?
In the same tensor.
Okay.
Yeah.
The dummy variables, I mean? They-
Yeah. So what I'm going to do is I'm going to consider this tensor. I'm going to consider S mu alpha. Then I'm going to transform it and then contract it. If I have to transform, so I'm going to consider this, right? So if I have to transform it, mu alpha, I want to end up with, I want to end up with mu alpha, sorry. So I'm going to do, what am I going to do? I need three index. Lambda,
Smiley face.
huh?
Smiley face.
Sigma, not smiley. But you make a good point. Smiley face is an index. It just means it sums through the four space-time index there is. Yeah, but we're going Greek. Sorry. So what's a good Greek index?
Iota, right? Is that one?
Oh, I don't know how to write iota. But I know theta.
Or you do pi.
So I'm going to do 3. I need to get rid of, I need to end up with mu alpha. Is that correct? And I need to get rid of what? See how it easy becomes. Wait till I say it's easy, then I make a mistake. Sigma, to watch for it every single time. That's what it is, right? And then what I'm going to do, so what did I do? I transformed it like they were not contracted. And then I'm going to contract it. So what did I do? Make alpha and mu the same thing. So then I'm going to go over here, mu lambda, mu sigma, mu theta, S lambda sigma theta. What is this? First of all, what is this guy? Isn't that the inverse matrix? So when I do this, I get lambda mu little lambda. What happens over here?
You get lambda mu sigma times the inverse.
Version must be lambda down. Sigma up
Well,
there.
let me put it, because we're getting started.
Times the inverse of, yeah, of mu over theta mu.
Okay, and then I'm going to write it as lambda mu little lambda, and just so that it is clear that we're doing matrix multiplication at this point, I'm going to write it as theta mu lambda nu sigma. Are you going to keep me straight?
Is it community?
Contraction. I mean, because everything is summed out. Everything is summed out in these two guys. None of these indices would appear on the other side. So if I do this, correct? It's the identity matrix. It's just S lambda theta theta. So if I transform and contract, it is exactly the same as if I contracted and I transformed it. So I have S bar mu nu nu so maybe I didn't make the question very clear, but let me do it. It's very important. If I didn't contract, but if and I'll clean this up in my notes if I'm able, but I want to make sure I'm conveying the right thing. If I transform a vector, see, initially it was alpha. So when I transformed it, I had 3 different lambdas. And then I contracted it. It is as if I contracted it first and then transformed it. So you can choose to contract whenever you want to. So when you see something like this, you should realize that that's just a vector.
It's just become a normal Lorentz transformation.
It's just a regular Lorentz transformation. Because nu has been summed out. Like for example, where did I sum nu out? If you see this over here, in your mind, you can do smiley face, smiley face. It has been summed out. It doesn't matter what's on the right-hand side. It's internally summed out.
Same with sigma and same with theta.
Yeah. Any index. But what you cannot do is a smiley face and what's the opposite of a smiley face?
Cry face.
Yeah, you can do that. You have to stick with it. What's the moral of the story?
No smiling, right?
That's not, but
Never smile.
never smile, but outside of that, the point is, if you contract and transform, it is the same thing as if you transform and contract. Meaning, contraction is a coordinate independent operation. If you have to contract, you contract whenever you want. Now you might say, well, it might be easier for me to contract before I transform, but that's not necessarily true, depending on. I can think of where it is not necessarily true, but the point is, contraction is a well-defined operation. You will find contraction to be useful in this chapter itself. Well, remember these. These are all the rules with tensors. I've been looking at 10-year applications. Yeah, with tensors. This is it. As bad as it gets, we would imagine. This is it. I lectured for half an hour. Beginning and end. Done. Finished. Remember these rules over and over again.
So that's all there is.
That is all there is to tensors. But we'll learn to take how to take derivatives of this. In flat space, there's no, in Minkowski relativity, it's just regular derivatives. This ends a very major part of the course. We begin with field theory right now. We'll do one lecture on the Klein-Gordon field, one, possibly 2 lectures on the electromagnetic field, then it's gravitation. We've collected all the tools necessary, right? These are possibly hard tools till you master them, like any other tools. Like I've said before, if you want to play a Beethoven piece, you don't start with a Beethoven piece. You learn how to play scales and you learn how to read music. That's exactly what we've been doing. We're on the verge of a symbol, maybe for release. All right. Klein-Gordon. I before E or E before I?
I've
for
said
you.
it.
I think for Klein.
Is that true for Klein?
I think for Klein it's
Klein
EI.
will be EI. Yeah. Naming is different.
EI, very
Yeah.
good, except for,
Naming is really like weird when it comes to.
We just don't talk about it.
it is a scalar field denoted by phi. On the one hand, it's the easiest field to understand. And we'll derive the field equation. Huh.
Klein.
John Mal's
Its origin.
Ah.
I think it's German, if I'm not mistaken, right?
And they have to be before one of those.
No, I looked at my notes, unless I made a mistake.
Is it German?
As long as you're consistent in spelling, we're good. So we had, this is, we won't spend a lot of time in this. This is just to talk about electrodynamics, and that is just to talk about gravitation, right? But it's actually very important. As simple, this is actually a very easy field. Even when you study quantum field theory, first you study how to quantize a scalar field. Makes sense, there are no indices. For goodness sakes, it's a function. Yeah? But it also turns out to be very important. The Higgs boson is a scalar field. In cosmology, the inflationary cosmology, the quantum field responsible for inflation of the universe, we haven't detected it, but we see its effects. We think it's a scalar field. The neutral pi meson is a scalar field. So it has a wide range of application. Hawking radiation that black holes radiate is completely determined by a scalar field. So you are on the verge of studying so many good aspects of physics. Yeah? If you were to pursue scalar field. But that's not the goal here. Our goal here is to study Einstein's equations. Okay? But you recall, I may have written with c squared multiplied this equation. I don't think I wrote it this way.
Isn't it F?
Oh, E.
You remember for a free particle with mass, I brought everything to one side and divided by c squared. And then I'm going to appeal to quantum mechanics to very quickly get to this answer. What is the energy operator in quantum mechanics? I h bar partial with respect to T, the Hamiltonian. I know I'm cheating. It's and what is momentum operator? Operator minus I h bar gradient. Is that true? let me make sure I'm not making a mistake. Yeah, that seems true. Aren't you taking quantum?
Yeah,
We're
it's
taking it
it's
now.
choice.
Taking is a strong word.
I'm in the class.
You're in the
We
class.
sit in there 9
I've just learned more about quantum in 2 seconds than I learned in that class so far.
Yeah.
Around 9 a.m.
I mean, you've seen Schrodinger equation.
Yeah,
Yeah.
we've done it in
We did that
a
in
different
water.
form. We did it in the
Heisenberg.
yeah, the Heisenberg, I think it's the Heisenberg?
Yeah, we did in the Heisenberg.
This is the Schrodinger representation, right?
Yeah, that's the Schrodinger representation.
Yeah.
And he said, this is what you'd normally see, this is not what
Yeah.
we're working with.
Ah, I see.
Yeah, we're not working
Oh,
with
you're
this
taking
one.
with Dr. Costa. Yeah, he will always give it to you in full force.
Yeah, that's one way to say it.
Okay, so I squared, I'm going to square this guy. I squared is -1, and there's negative will cancel out, and then I would have h bar squared over c squared. That's even great. So I can do, right? Just amazing how relativity and quantum mechanics talk until they don't. Minus I squared. Yeah, but the minus goes away, so I squared is negative h bar squared del squared plus m squared c squared equals 0. Well, I'm going to leave it in space. Well, this doesn't really makes any sense. It has to act on something. The simplest thing that it could act on would be
Yeah, we
It's
talked
minus
about
I squared,
huh?
so it becomes positive.
It should be plus 8.
No, it's negative squared. It's the negative sign squared and the I squared. Yeah.
You're right.
So it becomes
I mean,
positive.
I think
and
the negative and, as a matter of fact, because of my signature, but let me write it this way. First, but I usually have time to be the negative component, right? So I'm going, hold on. Easy to do on the board.
Should be the same.
Yeah. So the Klein-Gordon equation, it's a scalar field equation. It is given by, let me write it how we would normally write a differential equation, or in this case, a partial differential equation. CT squared, or if you even want, I mean, it's no real, like if I write it once, it should be clear. This is, of course, the Laplacian, right? Minus m squared c squared equals 0. Phi, of course, is a function of t, x, y, z, or I could perhaps, oh, it's a function of that. I could even write this as function of all the space-time. This is the relativistic equation of the scalar field. And now you would say, well, sure, that looks really nice. This is the definition of nice, by the way. But let me tell you why. First of all, look at this. Space and time is on equal footing. There are two derivatives of space. There are two derivatives of time. Better, even better, the c squared is over here. Yeah? So c times t is a spatial dimension. So it's just two derivatives of space, or space-time. There's a nicer way to write this. Oh, did I lose an h bar? Yeah. r squared. Oh, yes, throughout, right?
It should be
Yeah,
h r squared.
yes. And we'll show that this is relativistically nice, good, or covariant, or relativistically invariant equation. Okay?
How does that eta work?
Huh, that's a good, question to ask, and it's a perfect question to ask, because I have enough time to answer. Index is being summed
Over the derivative.
over the derivative.
So you've got,
Yeah. Well, why didn't anyone else ask that question? But let's go through it,
I knew Jackson would ask it.
because Jackson would ask that question.
yeah, okay.
Yeah,
That's why he's here, he asks questions for us.
All of them. That's all.
let's go through all the values of possible mu and u, because mu and u are being summed.
0, 0.
If mu is 0, mu has to be 0. And eta 0, 0 is -1. And then it is I don't want to write it twice, it is x0 squared, second derivative, because mu in this. Plus, now, because of what? If mu is 0, this is the only term that survives. If mu is 1, the only term that survives is the x. Mu has to also be 1.
So you can just put in a Kronecker delta there. You don't have to write all over technically.
I mean, well, that's
what that is, yeah.
that is. But if mu is 1, mu has to be 1. And when it's 1, the x1 coordinate, well, that's what we call x.
So eta works as a Kronecker delta for matrices, or not matrices, for the
it's
indices
not-
of mu.
No, I mean, so it so happens in special relativity, your nice and easy life is going to end very soon. I mean, this has been a cool breeze, I can feel it, right? Eta is not going to look so nice. But for us, yeah, it is diagonal. It's
And it starts with -1.
-1, then 1. So -1, then all the other space index. So make sure that is clear. So, I mean, when you write it, and in actuality, this is what it is. It is not so pleasant looking. This is just nice looking. And I'll show you that this is actually Lorentz invariant. If you write it in any other coordinate system, it'll look exactly like this. What do I mean by that? Watch this. That'll end up being the case. This is invariant under Lorentz transformation. You know it is invariant because there's no index to it. There's no free index to it. It's been summed out. This is a scalar operator. But we'll okay? But before I do, and that I'll confirm tomorrow. Or guys, actually it's in my notes, just go through it. It's very simple. Yeah? But let me state this. There's a simple solution to this. Some amplitude, e to the I can now write it as k mu x mu. Verify that this is a problem. Verify that this is a solution to that, provided k satisfies certain conditions. I want you to find out those conditions. I could have easily written this as A equals e to the eta mu k mu x mu. They mean the same thing. Find the conditions for k. Now I've asked a little more. Show that this is a eigenvalue to be Hamiltonian and the momentum operator. it's easy to see. If you take a derivative, it just comes out, that coefficient comes out. And is there anything you can say about the causal character? Work that problem, it's a good one. Well, I'll tell you what the causal character has to be. It has to be a time-like vector. After all, this is the energy of a massive particle. But you have to verify that. So I have shown that this, in the notes, I have shown that this is equal to this. Actually, you can even put this. But it's a scalar field, so what I mean by that is phi of x bar by definition. Scalar field has no components, so I don't have to multiply by lambda or anything like that. So verify this. And this is the problem that follows. So now we're getting to the point where you should be asked, when I come to class, you should be asking me good homework questions. Yeah, in this field, describes a lot of good physics.